after studying this module, you shall be able to know the brief description of classical thermodynamics, learn some thermodynamic terms needed under thermodynamics, differentiate between different types of systems, learn about different laws of thermodynamics, derive the relationship between enthalpy and internal energy of the particular reaction. Introduction. Thermodynamics. It deals with energy changes accompanying all types of physical and chemical processes or transformations not concerned with total energy of a body. Energy may be in forms, work, heat, light, mechanical or electrical, etc. Main objectives of chemical thermodynamics. Number 1. To predict the feasibility of a process may be physical or chemical under the given conditions of temperature, pressure and concentration. Number 2. To predict the extent of feasible process, thermodynamics has given certain mathematical relationships which can be employed to know the extent to which a transformation can take place before attainment of equilibrium. Number 3. To reduce some important laws of physical chemistry. Generalization of physical chemistry such as gas equation, law of chemical equilibrium, phase rule, distribution rule or law, Van 't Hoff's law of dilute solutions and Raoult's law of lowering of vapor pressure. Number 4. To deduce equations relating to some physical properties. Equations correlating the variations of certain physical properties, for example temperature, pressure, with others have been derived. From these equations, we can predict the effect of change of variable factors, for example temperature, pressure, etc. on different processes. Thermodynamic system and its surroundings. Any portion of universe or any portion of matter chosen for thermodynamics to study the effect of various variables such as temperature, pressure, volume, etc. is called a system. The remaining portion of the universe excluded from the system, which may be capable of exchanging energy and matter with it, is called its surroundings. The system is separated from its surroundings by real or imaginary boundaries. Types of system. Depending on the interactions between system and its surroundings, three kinds of systems are there. Number 1. Isolated system. A system which can exchange neither energy nor matter with its surroundings is called an isolated system. For example, a liquid in contact with its vapor in an isolated closed vessel is an isolated system. As the vessel is closed, vapor liquid can neither enter nor leave the vessel. That is, no exchange of matter from within the vessel with the surroundings. Further, the vessel is insulated. The system is not in a position to gain heat from or lose heat to its surroundings. That is, no exchange of energy with its surroundings. Number 2. Closed system. A system which can exchange energy but not matter with its surroundings is called a closed system. In the above equation, it is not isolated, then it is a closed system. Another equation. A chemical reaction taking place in a cylinder closed by a piston, mixture of O2 and H2 in the ratio of 1:2 by volume and closed in a cylinder by a frictionless piston. 2H2 in gaseous form combines with O2 in gaseous form will give two molecules of water in the liquid form, and delta H for this process is minus 285.9 kilojoules. So a large amount of heat is evolved. During the reaction, the volume of the gaseous reaction mixture decreases as the reaction is completed by the fall in volume. So, the piston moves down due to the some work being done by the surroundings on the system. The energy is in the form of mechanical work, has been transferred from the surroundings to the system. Thus, the system is in a position to exchange energy with its surroundings, but cannot exchange matter with the surroundings as the cylinder remains closed throughout. In the figure, it's a closed system. A liquid is in contact with its vapor in a vessel of constant volume and it is not insulated. This reaction taking place in a cylinder enclosed by a system is shown in the figure. Number 3. Open system. A system which can exchange matter as well as energy with its surroundings is said to be an open system. For example, expansion of water in an open beaker. The water in open beaker absorbs heat for evaporation from the surroundings and escapes into the surroundings as water vapor. The system exchanges energy and matter with the surface. Animals and plants are the examples of open system. Macroscopic properties. The properties associated with the macroscopic system consisting of large number of particles are called macroscopic properties. These properties are pressure, volume, temperature, concentration, density, viscosity, surface tension, refractive index and color, etc. State of a system and state variables. State of a system. The state of a system is defined when its macroscopic properties are specified. When macroscopic properties of a system have definite values, the system is said to be in definite state. Whenever there is a change in any one of the macroscopic properties, the system is said to change into a different state. State variables. The macroscopic properties of a system are often called state variables, since the state of a system changes with a change in any of the macroscopic properties. For example, pressure, temperature, volume, mass, and composition. For defining a state of a system, it is not necessary to define the values of all state variables since they are independent. In homogeneous system, these properties are interrelated by equation of the state PV is equal to RT, where P is pressure, V is the volume of 1 mole of gas, R is the gas constant, T is the absolute temperature. The value of any of these pressure, volume or temperature can be calculated provided those of other two are known. They are independent variables. Two variables generally defined are temperature and pressure. They are independent variables. The third variable V is called dependent variable as its value depends on temperature and pressure. In closed system consisting of one or more components, mass is not a state variable. State and path functions. Work and heat are path functions. Value of Q and W depends upon how the process is carried out and which rule is adopted. Delta U is integral of du from initial to final state. Delta U depends on initial and final states of system but is independent of path. Therefore, it is a state function, exact differential. But Q cannot be written as QF minus QI because it depends on path. Therefore, it is a path function or inexact differential. Zeroth law of thermodynamics. This law states that two systems in thermal equilibrium with a third system are also in thermal equilibrium with each other. First law of thermodynamics. Work. Work is defined as any quantity that flows across the boundary of a system during a change in its state, and its effect is noted in the surroundings in the form of either weights are higher or lower in the surroundings. Work done on the system is positive, work done by the system is negative, and its units are joule in SI units, and 1 joule is equal to 10 to the power 7 ergs. Heat. Mode of energy exchange between the system and surroundings, which results from the difference in the temperature of the system and the surroundings. Its units are calories. A calorie is the quantity of heat required to raise the temperature 1 gram of H2O through 1 degree Celsius. If system has absorbed heat from its surroundings, then Q is always positive. If system has given heat to the surroundings, then Q is always negative. All other forms of energy tend to change ultimately into heat. Internal energy. Every substance is associated with a definite amount of energy, which depends upon its chemical nature as well as upon its temperature, pressure, and volume. This energy is known as internal energy. Exact magnitude of this energy is not known, since the chemical nature includes translational, rotational, vibrational moments of the molecule, nature of individual atoms, arrangement and number of electrons, energy of nucleus, etc. Internal energy of a substance system is a definite quantity and is a function of only of the state, that is chemical nature, temperature, pressure, volume and composition of the system at the given moment, irrespective of the manner in which that system has been brought out. Equivalence between mechanical work and heat. Work can be converted into equivalent of heat energy. If W is a mechanical work, that is proportional to H, that is heat produced. So W is equal to JH. When this proportionality sign is removed, then it is replaced by a constant J, which is known as Joule's mechanical equivalent of heat. When H is equal to 1, then W is equal to J. So J is defined as the amount of work done to produce the calorie of heat and is numerically equal to 4.184 or 4.184 into 10 to the power 7 ergs, where 1 calorie is equal to 4.184 joules. First law of thermodynamics. Energy can neither be created nor destroyed, although it can transform from one form to another. Energy can be produced by the destruction of mass, the two quantities being related by the expression E is equal to mc square, which is the Einstein equation. The modified law. The total mass and energy of an isolated system remains unchanged. The mathematical formulation of the first law of thermodynamics is: suppose a system is subjected to change of pressure and volume. Let initial state be A and the final state represented by B. UA and UB are the energies associated with the system in its states A and B respectively. Change in internal energy delta U is no doubt equal to UB minus UA. Energy change accompanying a process is a function only of the initial and the final states of the system. and is independent of the path by which the change is brought about. Energy changes in relation to work and heat changes. UA is the energy of system in its state A. UB is the energy of system in its state B. Suppose the system, while undergoing change from states A to B, absorbs heat Q from the surroundings and also performs some work, mechanical or electrical, equal to W. The absorption of heat by the system tends to raise the energy of the system. The performance of work by the system tends to lower the energy of the system since it requires expenditure of energy. So delta U would be equal to UB minus UA equal to Q minus W. In general, if in a given process the quantity of heat transferred from system to system is Q and work done in the process is W, then delta U is equal to Q plus W. Since the work done by surroundings on the system, W is always positive, and if the work is done by the system on the surroundings, then W is always negative. State functions. State function has a definite value for a particular state of the system. It is independent of the manner in which the state is reached. It depends only on the initial and the final states of the system and not on the path. For example, pressure, temperature, volume and delta U, that is change in internal energy. W and Q are path functions. So if du is equal to u2 minus u1, which is under the integral values ranging from u1 to u2, but dq over the integral q1 to q2 is not equal to q2 minus q1, or dw over the integral from w1 to w2 is not equal to W2 minus W1, which is an inexact differential. Enthalpy of a system. Let change of state of the system is brought about at constant pressure and there will be a change in volume. Let increase in volume occurs from VA to VB at constant pressure. So the work done by the system W is equal to minus P into VB minus VA. Since according to first law of thermodynamics, delta U is Q plus W, so therefore we can write delta U equal to Q plus minus P into VB minus VA is equal to Q minus P VB minus VA, or UB minus UA equal to Q minus P into VB minus VA, or we can write UB plus P VB minus UA plus PVA equal to Q. The quantity U plus PV is called enthalpy and is designated by H. So we called as H equal to U plus PV, that is, it represents the total energy stored in the system. Since U, P and V are definite properties, therefore H is also a definite property. HP minus HA equal to delta H is equal to Q, which we can get from equation. Since UB minus UA equal to Q minus P into VB minus VA, since Q is equal to delta H, therefore delta U is equal to Q minus P delta V, or delta H is equal to delta U plus P delta V. Summary. Thermodynamics is that branch of science that deals with energy changes accompanying all types of physical and chemical processes or transformations. There are three types of systems depending upon the interactions between system and surroundings. 1. Isolated system. A system which can exchange neither energy nor matter with its surroundings is called an isolated system. Number 2, closed system. A system which can exchange energy but not matter with its surroundings is called closed system. Number 3, open system. A system which can exchange matter as well as energy with its surroundings is said to be an open system. First law of thermodynamics states that energy can neither be created nor destroyed, although it can transform from one form to another. Mathematically, the first law of thermodynamics can be written as delta U equal to Q plus W, where delta U is the change in internal energy, Q is the change in heat, and W is the amount of work done during the course of reaction. Enthalpy is the state function which represents the total energy stored in the system. The relation between enthalpy and internal energy is given by delta H is equal to delta U plus P delta V.